So we're working now in hyperbolic geometry. And we said that if we have a line segment and a point not on that line, or so line, not line segment, we know that there are parallel lines, which are the first non-intersecting lines on either side here through the point. And then there are an infinite number of other lines through the point that do not intersect the line in question. Okay, and we said that if we draw perpendicular right here, these are our angles of parallelism. Okay? We also said that these parallel lines, or sensed parallel lines, remember, parallel specifically means these are the ones that have this angle of parallelism. The other ones we say non-intersecting or ultra-parallel. These intersect at an omega point or an ideal point. We often use omega to represent it. So an ideal point out here. And you should have seen the video talking about the Poincaré model. The Poincaré model gives you a way to kind of picture those ideal points. So if we have if we have this case, then we can understand a lot about parallelism in hyperbolic geometry by looking at triangles, but not just regular old triangles. We can think about points A and B, and we know that this, if we have a line through B, any line through B, then if we can take the parallel through A, and they must meet at some ideal point out here. Okay? And so we call this an omega triangle, or an asymptotic triangle. Okay? So an omega triangle has some interesting properties, and the study of omega triangles can tell us a lot about hyperbolic geometry and the way parallel lines work. So it's this three-sided figure. 2 points are points of the geometry. 1 point is an ideal point. Okay, and these lines this is the sensed parallel lines. Now notice this angle right here. This is not the angle of parallelism, because we're not guaranteed that AB is perpendicular to the line through B. We call this B omega. Okay, because AB is not perpendicular necessarily, it's not the angle of parallelism. We only define the angle of parallelism when we have this perpendicular right there. Okay. So a first result to discuss is that we talked a little bit last time. We mentioned the axiom of Pasch. It holds for an omega triangle. And as a reminder, just in Euclidean geometry, the axiom Pasch basically says if you have a line through a vertex, it has to intersect the opposite side. Or if it enters through a side, it has to intersect one of the other two sides, or the opposite vertex. Okay? For an omega triangle, whether the line enters at a vertex or at a point not on vertex. Okay? So in order to investigate this, let's just consider some point. Let's let C be a point. Now let me say that slightly differently. We'll say an interior point of omega triangle AB omega. Okay, so I'm just considering some point C right here. Okay. Now, if we look at this line BC, what we want to show is that BC has to intersect A omega. All right. Okay. So why must it intersect the omega? Well, we know, or A omega, we know that these two are parallel, right? So the first parallel line through B to A omega is B omega. So if this is interior, this has to intersect A omega, okay? So it has to intersect because this is the first non-intersecting one, okay? So then BC, by the same argument, AC has to intersect B omega because A omega is the first non-intersecting line to B omega. So this is where this notion of parallel as using the first ones is helpful. Okay, the first non-intersecting lines. Then BC and AC intersect opposite sides because B omega is the first non-intersecting line to A omega through B, and I'm just going to say similar for AC and A omega. Okay. All right. So, like we just said there. Now, the other option here is it could come through the ideal point, right? So what if it comes through this ideal point right here? Okay. So what we need to prove is that C omega intersects AB somewhere. Okay. So we can say if C omega enters the omega triangle through the ideal vertex, okay, then we can just apply Pasch's theorem to triangle ABC, okay, or then it intersects AB by applying axiom of Pasch to triangle ABC. Okay, and then we're done. Okay. Now we can actually go the other direction as well, but for now, we're just going to leave it there. We've shown that if it intersects, it goes through there. So there's kind of more to this. The second part of the proof is an exercise in this section, so I'm going to leave it to do on that. Okay. Now, there's a couple other theorems that I want us to investigate, but I'm actually going to leave it up to you guys to read the proofs and present the proofs to each other, which is an activity we would do in class if we were in class together. So we're going to do it virtually using Flipgrid. Both of these correspond to things we know in Euclidean geometry. So, for example, for the first one, in Euclidean geometry, we know that the measure of an exterior angle of a triangle is greater than the measure of either opposite interior angle. Okay, and this is actually true in is in what we call neutral geometry. We don't need the Euclidean parallel postulate in order for this to be true. So this actually holds in hyperbolic geometry. So the way Euclid proved this is he said, well, let's take ABC. Okay. And what I want to show, we want to show that the measure of angle ACD is greater than the measure of angle, let's say BAC, to start. We could do either one, but for now, we'll do it. So we'll just do that one, and then you can just do a similar construction to find the other one. So the proof here was to look at the midpoint here, okay, and then take a line through this point, we'll call it E, and we construct it so that these are the same length, okay, and then that's going to give us some point F out here, and we can construct this right here, okay. So if we have that, then we have vertical angles, we have things that correspond here, so we have triangle ABE is congruent to triangle CFE by side angle side. Okay. Well, if that's the case, then the measure of, or we'll just say angle BAC is congruent to angle FCA. Okay. But F is on the interior of angle D or ACD. So we just get that the measure of angle ACD is greater than the measure of angle FCA, which is equal to the measure of angle BAC, which is what I wanted to show. Okay, so that's the proof here, and that this holds in hyperbolic geometry if we have 3 points in the geometry, and we're actually there's a corresponding theorem for omega triangles specifically. Okay, so where we have one of our vertices is an ideal point. So it says that for any omega triangle AB omega, the measures of the exterior angles formed by extending AB are greater than the measures of their opposite interior angles. Okay, so what we're saying here is that if we have an omega triangle and we extend this up like so, okay, so let's call this C and this D, okay, so they're saying that the measure of this angle must be larger than this, so the measure of angle CA omega is greater than the measure of angle AB omega, and the measure of this angle must be more than the measure of this angle. Okay, so the measure of angle DB omega is greater than the measure of angle BA omega. Okay. Proof of this is on page 376 and 377 in your book. I'm going to split up the class so that some of you prove this and some of you prove the other. The proof is there. Your job is to read through it and explain it as if you're teaching it to the class. Okay. The other theorem that I want us to look at is think about triangle congruence. We know that we have side angle side congruence, that two triangles are congruent if an angle and the sides that make it up are congruent to each other, so side angle side, and from that we can prove some other triangle congruence criteria. Angle side angle, right? Angle angle side, so forth and so on. Side side side. So how do we prove that omega triangles are congruent? So one theorem that we can use to prove this is we can say that if, let's say we have omega A, B, and then we have some correspondence here with A prime, B prime, omega prime. Okay. Well, it turns out that if I can prove that these sides, or those segments, are the same, and one angle, doesn't matter which one, is congruent, that is sufficient to get that the omega triangles must be congruent. In order for the omega triangles to be congruent, we need the only thing left to prove is this other angle, right? Because everything else are not really lengths to look at, right? These are lines that extend off to some ideal point. So as long as we have these three pieces being congruent, we have omega triangles are congruent, and this says that if I know two of them, one side and one angle, that'll be sufficient. Okay, so the theorem here is that omega triangles AB omega and A prime B prime omega prime are congruent if the sides of finite length are congruent. In other words, AB is congruent to A prime B prime. Okay. And if a pair of corresponding angles at A and A prime or B and B prime are congruent. That is let's say that bad, measure of angle A equals measure of angle A prime, or measure of angle B equals a measure of angle B prime. Okay, so this is one congruence criteria for omega triangle. This proof is on page 377. And again, a subsection of the class is going to look at that one as well. So your task for today is to catch up on all that we're doing here, and then to present your assigned proof on Flipgrid to the rest of the class to kind of explain and walk each other through it. And then we'll be able to watch each other's, give some feedback, and all land on the same page. And hopefully understand a little bit more about omega triangles. And again, that's one reason I want you guys to presenting the proofs, is because it helps you kind of gain more experience and understanding with how these things work, because they're a little bit non-intuitive. They're outside our realm of experience a little bit.